In today's lesson, we're going to be looking at the frequency polygon. So this is going to be kind of an introduction or a bridge lesson to kind of help us understand what we're going to be doing in kind of, again, like I said, a future lesson. We're going to be looking at how we can go or how we can approximate certain continuous distributions of data. So an introductory video, if you want, you can go to YouTube, take a look at the honeybee and the hexagon. It's a small animated TED Talk. It looks more at just how honeybees use polygons to kind of approximate or give us a close value for what they're looking for. In our case, we're going to be using polygons to approximate something else and not beehives. So the frequency polygon, the main thing that we're looking at, basically what it is it connects the midpoints of the tops of all the bars on a histogram, creating a polygon that approximates the frequency histogram. So we see this line here. Let's kind of go over it. This line here specifically is our frequency polygon. Now we're going to be recreating this graph, so I'll show you how you can create it. And you can do it where the histogram isn't there, or where the histogram is, so you can kind of see how it does get formed. But the frequency polygon is pretty much the line that connects all the midpoints of the tops of the bars. And again, it approximates the rough shape of our frequency polygon. So roughly the parts that are above and below, or the gaps in between. So say, for example, if I look at this part here, that kind of is balanced out by this part here, here, and so on. So it's all kind of balanced out in terms of what's above and what's below. So we're going to recreate that frequency histogram and polygon for the CO2 emissions in the United States. So again, those the data for it is available in our course content, but I will bring it up here. So basically it opens up a PDF, or sorry, not a PDF, an Excel sheet that has roughly like 400 values or 400 different data points in terms of millions of CO2 released per year by coal plants. So the thing with creating a frequency polygon is that we need to use GeoGebra. So I'm going to collect my data. I'm going to basically click the A value or the top to highlight everything, and I'm just going to copy all of this data. I'm then going to open up GeoGebra Classic, similar to what we've done before. So we go to geogebra.org, we go look for Classic, and we'll open up. The main thing that we need specifically is a spreadsheet. So if I go over to this little symbol and I click on it, I should get the option somewhere, maybe it's over. I should be given the option, oh, there we go. If I click the three dots, I want the option for a spreadsheet. I'm going to move kind of these windows over because I don't really need them too much. I'm going to click in the first box and I'm just going to click paste. It might take a while to load your data, and I found that it doesn't always show all of the data, but it does give us the right answers for what we want to do later. So for example, I can't really scroll down when I'm zoomed, but again, we're going to trust that it's all there from copying and pasting. We're again going to highlight all of our data. I'm going to go up, and I want to create a one variable analysis because I'm only looking at one variable here. I'm going to ask that it creates a histogram. So we've gone through these steps before to create a histogram. Now what we're going to do is click on this little cogwheel, and it's going to give us some options of what we can do. And we might have to zoom out a little bit. We can see here, it gives us the option of what we want to show. Whether we want to see a frequency table, so if we want to see what the frequency is between each bar, so I can see that in this bar of 2.02 to 2.6, there are 13 values, 2.6 to 3.17, there's 83 values, and so on. I can also then create a frequency polygon just by clicking on this next one. So that's what we do here, and again we can see our frequency polygon. If I click the histogram and take it away, again I have an approximation of what my histogram is. What I'm going to do though is I'm going to manually change my interval size. So I'm going to click this, set classes manually, and it gives me the option to change it. So I'm going to change it from a width of 5 to a width of 1, and I want you to see what happens to the graph. So there I've changed it to 1, so now I only really see 2 values. And I can see quite a large number of them are in the middle one. And now I'm going to do 0.1. Get an idea again of what it looks like. Again, we can see our frequency. It's more spread out now. We kind of see it clustering in the middle. I'm going to go to 0.001. Oops, too many. Click out. It might take a while. Again, it is an internet software, so it might take a while. And here again, I can see it's very spread out, and I really don't get a good sense of what my data is. And if I can, give it some time, if I scroll down, I can see that really none of the values really passed 1. We have about maybe a couple that are at 3 and a lot that are at 0 or 1. So we really don't get a good representation of it. So again, it's just going over that idea that changing our interval size can get us a better view of what our data looks like, as well as if we go too far in the one direction, making it too small, we're not going to get a good representation. Same as if we go too big. So again, it's that idea of you have to play around with the data or with your interval sizes to get something that looks nice and it fits. Again, you could look at it based off of the values that you're dealing with, how many decimal places your data points have, how many data values you have in general, and things like that. So going back to our lesson, the area under the polygon. So we've talked before about how when we deal with continuous data values, you want to find the area underneath the bar or of the bar to represent the probability of a value or of it being in that specific interval. And we can change our frequency histogram or polygon so that the area under the line determines the probability of a data point landing in a certain interval. Because right now it's just the frequency, how many data points we have in that interval. It's not the probability distribution yet, like we looked at in the last lesson. And again, basically it's using a bit of calculus in there and some higher math functions, but we're not going to get into that too much because we're going to let the computer take care of that for us when we get to it. So what we're going to do is we're going to use the same frequency histogram from example 1. We're going to set it to an interval size of 0.1. We're going to have it start at 1.9, and we're going to display the frequency table, histogram, and polygon. We're going to change some of the settings. We're going to change it from count to relative, see what happens, and then to the shape and the vertical axis, and then we're going to calculate or find the probability that a coal plant is between 3.6 and 3.7 million tons of CO2 emissions. So let's go back to our table. Let's zoom in a little bit if we can. There we go. Oops. So I'm going to change it from count to relative. And when I do that, I want you to take a look at our graph. Let me see if I can close out. No, I can't really close it. There, we'll close out some of it so we just see our graph. I'm going to change it from count to relative, and I want you to tell me I want you to take a look at the graph and see, is there anything that changes? So by looking at the shape of the graph, notice that the shape doesn't change. I'm going to go back again. hopefully you can kind of see what's happening. And what's happening is we're actually changing the vertical axis, and now the vertical axis represents the probability. What's the probability of a value or of a data point landing in these specific positions? Right, so we have our different probabilities of it being within a certain interval. So what is the probability of it being between 3.6 and 3.7 million tons of CO2 emissions? So if I go to 3.6, it's 3.5, 3.6 to 3.7. So if I look at this one, or if I go down to my table, 3.6 and 3.7, there is a 7% chance that a coal plant is between those two values. Now what I'm going to do is I'm going to change from relative to normalized. So if I go to normalize, let's see what happens. And again, pay attention to the shape of our graph and the axes. So I'll do it again to see if you can see the change. So when we see the change, what's happened now is that now this value here actually tells me, or we've changed the value so that when we find the area of the bar, that now gives us the probability. When we did the relative, all we needed to look at was the frequency on the side, or the value, the vertical value, that told us the probability. So this would be kind of similar to a combination of kind of our discrete and continuous probability distributions. When we go to normalize, this is specifically just a continuous distribution, or a continuous probability distribution, because the area of the bar represents our probability. So if I go down to 3.6 to 3.7 again, and I see that height, or that vertical value of 0.74, what I can do now is that when I find the probability, it's actually the area of that bar. So the area, or the width, you could say, is 0.1, because we know that's the interval width. And let me see if I can't highlight it here, but we can see here. So the width is 0.1, the height is 0.74, and when I multiply those together, I get 0.074, which is the same thing as saying a 7% chance. A few more decimals here because we are kind of changing it a bit, but roughly still it's the same percentage or same probability of an individual or of a value or coal plant falling within 3.6 and 3.7 million tons of emissions. So again, that's the difference between the three. Count is just our frequency, how many data points fall within. Relative, again, the height tells us the probability, and when we normalize it, the area of the bar tells us the probability. And the reason we get to that is because if I have the area underneath the line representing the probability, if I look just at the polygon, and if I have a function, or I come up with a function for this line, then I can use that, and I can use calculus and other higher level math to determine what is the probability of something falling within a certain interval. Or I can start to use the equation of this line to predict. So again, that's kind of our goal, or that's the reason why we get to this, is because I want to be able to predict the probability of a certain value point or a certain data value falling within a specific interval, or what's the probability of having a certain amount, or so on. So that's kind of the goal, basically, just understanding what we're doing, how we're going from a frequency to basically a normalized, where we have basically a probability density or a probability distribution. So again, just kind of the math we did. The relative one, we just had to find the height of our bar. The normalized one, we actually had to find the area of the bar. And while it may be easier to do the relative, looking at a graph, normalized is better in the end, because if we come up with an equation for that line or that polygon, we can use some higher order math to figure out the actual or predict probabilities. So here we're just looking at the different ones. Again, it might be hard to tell, but again, we know if I kind of zoom in here very far, we can see again that it's the vertical axis that's changing. The shape of the graph doesn't change. So this table again is just looking at the different things that we went through, looking at the histograms and the polygons, and what they're used for. So a frequency histogram, our very basic one, displays the intervals in which the data point lies, so that's our x-axis, and the total number of data points in each interval, or our y-axis. And this is basically just shown, or it shows the distribution of the data and the modal interval. The frequency polygon again connects the midpoints, and it just approximates our histogram, which is basically all that it does. The relative frequency histogram, so this was the second one we created. Again, it shows intervals for the x-axis and the percentage of points, or the probability of it being in each interval, or the y-axis. So this shows the probability that a given data point lies in one of the given intervals. The relative frequency polygon, so basically if we kept the polygon for that shape, again it connects the midpoint, so it's doing the same thing, and it just approximates this relative frequency histogram. We don't really use it for much. We don't use it for anything really until the last one. Then finally, the probability density histogram, or the normalized one as we called it, that displays the bars in a way that their areas are equal to their probability or percentage. And the use of this, it's used basically to create the polygon. And the polygon is useful, again, still connecting the midpoints, but it's useful because now it can be approximated to find the area of any interval. So any interval that we want, it doesn't just have to be specific to the intervals we have. If we approximate that polygon, we can use higher level math to determine the area of a specific interval, or the probability of a specific interval. And if we can come up with an equation for it, then we can use that again to predict or estimate certain values. So the main goal is basically to transition from our histogram to our probability density polygon. And the main thing that we're going to be doing with this is looking more at a normal curve, because a normal curve is specific, or a specific type of continuous data, or the way it's distributed, that's very useful. So if I go back to my graph or my histogram, if I click on normal curve, or that option for normal curve, it will give me what the normal or a normal distribution is. And we've talked a bit about that before. And a normal curve is useful due to the specific properties, because the specific properties are, we know for sure what percentage of values lie within specific parts. We talked about standard deviation. As more specifically, there is an actual chart that shows the areas of all possible values, regardless of what we're looking at. If it fits a normal distribution, there is a specific chart that applies to that specifically, so that we can kind of approximate or determine the probability for any value of a given point or given data point. So I'm just going to show you that quickly. So if we go back to our Sorry, let me bring up our histogram. So we go back to our histogram, and if I click on this normal curve, again, we see how the data generally kind of follows that normal curve. I take away kind of that frequency polygon, we can see it. Click back. Yes, again, following the bars, but it does tend to follow that normal curve or normal distribution. And that's what we're going to look at in future lessons of how we can actually use that normal distribution to help us determine probabilities and predict and things like that. So again, the main thing in this note is just understanding what a frequency polygon is, how to create it in GeoGebra using given data, and basically the difference between count, relative, and normalized in terms of what they represent or what they show us.